at development of equation inside the flow. Okay. So just now we mentioned, before we stop, we mentioned that the fully developed flow, we're going to define the velocity in terms of r from the center line here. Okay. Now we look further into the diagram that you see on the screen. You see on the left hand side, you're having a parabolic profile there. The parabolic profile given you an equation. V equal to U in terms of R. U in terms of R distance. U in terms of R means there is an equation that link the R with the velocity. I, what mean by I hat is a vector form. So I hat vector form usually link with the x direction. So as you can see, there's a small x at the center of the pipe. So for pipe, we always refer to the center of the pipe and the direction. You need to be careful. In this case, we're using x direction. Okay, x direction. That's why equation here is U, R, and I hat. So we are looking at what is happening to this cube here. We're going to look at what's happening at the cube here. And this element, or we call it control volume, this control volume that we studied before this in chapter 2, now we use it in the pipe. So this control volume is having a length of L and the total diameter is D. So we're going to look at what happened at the T is the solid line, and after there's a change of time plus delta T, the dot line happening as what's sketched in the diagram. Okay. So there are three ways to develop equation. First, we use second Newton law, F equal to ma, which is the first one. Second one, we're going to use nervous stroke equation of motion. Third one, we're going to use dimensional analysis method. So if we have time, I will go detail on nervous stroke. If no, I will just ask you go and read and you memorize the equation structure for nervous stroke, because nervous stroke equation is a lengthy equation, right? However, there's some pattern that you can memorize for nervous stroke. For dimensional analysis, this one it will come into our last chapter of this module. We'll look at analysis method, dimensional analysis method. So for this session, we'll use second Newton law, F equal to ma. We look at the force. We'll convert all the pressure along the cube here, or the rectangular here. We'll convert pressure into force, and then we were going to use F equal to ma to develop the equation. All right. So I already covered what I mean by all the parameter: time, length, radius, and diameter. These are the parameter that we're going to use. And now we are using the first approach. We will use second Newton law, F equal to ma. And the most easiest way when we solve second Newton law is equilibrium, means all the force inside the system equal to 0. Okay, the trick or the key to memorize F equal to ma approach is all the force equals 0. Okay, all the force around the system that we study later on will be equal to 0. And we convert all the parameter inside the pipe that we can find, change them to forces. For example, in pipe, just now, the first session, I already teach you what is open channel and pipe flow. Okay, pipe flow and open channel. Pipe flow is because of pressure. Open channel is gravity. So when you look at pipe flow, you look at pressure. So convert pressure to forces. Okay, definition of pressure is force time divided by area. So to convert back to force, force will equal to pressure times A. Okay, so these are the concept that you need to be careful when you derive equation F equal to ma. Just make sure your steps is all the force equal to 0. Then you manage to find the answer. Okay. All right. So in this case, yeah, we know that since we're having parabolic, then we're having a non-uniform flow. So one thing about fully developed and steady condition, this will be a key point or keyword inside the problem statement or inside the question. If you see that you're having a fully developed, what does it mean? It means same distortion of each end of the fluid element, means they change the same orientation. Okay, or you can say that the distortion means if this is point 1 is having this profile, point 2 also having the same parabolic profile. Okay, it means that when you have a fully developed and steady, means that you have the equation for this profile you can use for 1 carry forward to 2. Second one, if you have a steady developed, acceleration equals 0. There's no acceleration. What the definition of acceleration? Velocity divided by time. Okay, so since you are steady, when you are steady, the rate of change of your velocity is 0. Okay, when it's steady, the rate of change of your velocity will be same because v here will same as v here. V at 1 will same at V2 at the center of the pipe. Okay, so the rate of change from point 1 to point 2 will be 0. Okay, so these are the important concept. Okay, so velocity profile. This is a bit complex where you will see in nervous stroke equation, but at this moment you just have a look in this equation at the bottom of the screen. When you have a fully developed and you deal with nervous stroke equation, then you will see this form of equation. V dot and the inverted vector equal to U partial differential of U divided by X along X-axis in X-axis equals 0. Meaning the acceleration along X-axis is 0. Okay, this equation it just means that AX, acceleration in X direction, equals 0. This is a mathematics equation when you deal with nervous stroke equation. Okay, so this point we already covered. The third one is also I mentioned, constant velocity inside the pipe. If you draw streamline, okay, in chapter 1 we talked about streamline already. So what mean by steady and fully developed mean if you draw the streamline, you have a straight line inside the pipe. Okay, don't confuse streamline and velocity profile. It's a different things. Okay, so but by observing the streamline, you can see that this behavior is called steady. Okay, it's called steady flow. Okay, look at the center of the pipe here. I label with the box of red color line here. So what are the assumptions when we develop or we use the F equal to ma equation? First, there is no gravitational effect in our equation, meaning we take out the G effect. Gravitational force is going to move down. You're going to move all the mass of your fluid going down. However, in this case, we ignore the effect of gravity. Okay, yeah? When we derive F equal to ma equation for laminar for flow inside pipe, we ignore the gravitational force at this moment. As we go deeper, gravitational force we're going to add into our equation. At this moment, we will not consider gravitational force. Okay. At this moment, we are looking at straight pipe. Later on, next week or next lecture, we're going to look at a pipe that's slanted with an angle, theta. Next lecture. So far, we deal with straight pipe. So straight pipe, gravitational, we do not consider. Gravitational force, do not consider. However, when it comes to angle, then you need to read carefully on the question. Sometimes you need to consider, sometimes you don't need. All right. F equal to ma, second Newton law. And I pull the red box into a separate area here. So if you look at the box here, this box represents the fluid inside our control volume. On the left-hand side, point 1, you have pressure times area. Area of a cylindrical pipe is a round circle. So that's why we can use area equal pi r square. Or in this case, you see a small r because we are referring to small r here. Okay. On the left-hand side, P1 times pi r square. On the right-hand side, there is a change of pressure, negative delta P. P1, P2. And recall why there's a negative delta P there. You remember just now I asked Q on one question on the flow direction, Q, in the pipe flow. Q give the reading of two pressure here. Pressure 1, pressure 2. So to make the flow from point 1 to point 2, pressure 1 must more than P2. Must be high pressure at this point. Meaning, if you look at this scenario, this diagram, the flow, you look at the velocity profile, the direction is from the left to right. So it means that P1 is more than P2. So to define P2 in terms of P1, we write P2 equal P1 minus delta P. To represent P2 is less pressure than 0.1. Okay, we are now dealing with pipe flow. So pipe flow, we already introduced from the pressure reading itself, we can know the direction of the flow, or Q, volume flow rate. And how do we know the direction? Also, you read from the velocity profile here, the arrow pointing from left to right. So you know that P1 higher pressure than P2. That's why you can write P1 minus delta P. Delta P is the change of pressure times the area. You get the pressure on the left-hand side. And the arrow is pointing into the surface. Remember, we deal with pressure. Pressure force always pointing to the area or surface. Pressure always pointing to the area. And when you convert pressure to forces, okay, you take, okay, pressure definition, force divided by area. You calculate force, you take pressure times area. So convert this pressure into force. You take pressure times area. What is the area? This area. The pressure act on the area. So same with this one. And the arrow is pointing to the left. Careful, huh? And in this case, there's one new parameter that you see on the diagram here, which is the mu. You see the mu here? There's a mu. We call it shear loading. Okay. What I mean by shear? Basically, you know that water, you can say as okay. Let's say you have a jelly float. Okay, you making a jelly. So when you have a jelly and you push this jelly from left to right inside a container, so this jelly is going to change shape to become something like that. Okay, because this one stick to the wall, so this one cannot move. So it's going to change shape to something like this. Okay, you're going to change shape like this. So if you have a force that is parallel to the surface, if you have a force that parallel to the surface, you are having a shear loading. Okay. So again, recall back. So if the force is perpendicular to the area, this scenario gives you normal stress. Normal stress. Normal means 90 degree, normal stress. Second scenario, it doesn't change the force and the area, but I tilt the force. When the force is parallel, same direction of the area, this combination will give you shear stress. What is the equation for stress? F divided by A, or similar to pressure. This is to get the normal stress. Shear stress, because the word stress is there, same, F divided by A. So only differences between normal stress and shear stress, if you use the word shear, it means the direction of the force is parallel to the area. Okay, parallel to the area. Now, if you have a shear loading on the surface here, how you convert shear stress into force? What you take? You take shear stress times area. Okay, by using this equation, shear stress equal to force divided by area. You convert shear stress back to force. It become a shear force. Shear force, you take shear stress times area. So in this case, how you calculate area of the shear is the area of the circumference. You take this circumference times the length, you get the area of the shear stress, because shear stress acting along the surface. So in this case, inside the pipe, where does the shear stress work? It works along the surface, and it go against the flow direction. You can treat shear stress as your friction force. So friction force act along, or shear loading, it get along the surface. So how you calculate the surface for cylinder? You take the parameter, which is 2 pi r, which is the parameter, times the length, you get area. So you get shear stress or shear force by taking shear stress times the area. You get shear force at the top of the diagram. Okay, yeah? Ask me a question if you don't understand what is this, you don't understand why this one suddenly there's a negative delta P, why we need to times pi r square, why you don't understand what is this, you don't understand what is this, huh? This is a shear stress component that happen in the fluid because the water usually have a shear behavior. Okay, like a jelly, you push something, you will have a layering of behavior. So at the wall there, you can see like a friction effect that the shear stress will act on the surface. So you take shear stress times area, and this one is 2 pi RL. Okay, so from the diagram, we are seeing three forces, and the x direction is positive to the right, and you are using all the force equal to 0. Okay, I'm going to give you the equation that you see on the screen. The first one is the pressure component that acting on the both sides of the control volume. P times A minus point number 2 times A. Y negative because the arrow is pointing opposite to the reference axis of X. That's why you have a negative sign here. And Y negative sign for shear stress or shear force is because the direction also opposite of the X equal 0. Then the next question you need to ask yourself, from F equal to MA equation, this, let me change the color. This component is all the force in X direction. And since we have a steady flow, the A component 0, that's why 0 times mass, you get 0 on this side. Okay. So from here, you are having pressure, having pi is a constant, you're having the R, you're having the L. Okay, so we're going to use this equation to develop the relationship between pressure and radius. Okay, there's a note there. So as you can see, the pressure is proportional to R square. If, all right, relationship within shear and R also same, right, proportional to R and so on. Huh? Okay, the next one, you rearrange the whole equation. You rearrange this equation. You will arrive at the ratio, pressure ratio, delta P divided by L equal to 2 shear stress divided by R. Okay, this one you cancel. 2 pi cancel. You rearrange the equation, you get this one. This is useful information when you solve flow inside the pipe. P is the pressure, change of pressure divided by length equal to 2 stress divided by R. So by using this F equal to MA, the product of F equal to MA and steady flow assumption, we arrive at the ratio where it will help you to calculate if you're given the L, the length of the pipe, you're given the shear stress value, you're given the R value, you're able to find the drop of the pressure inside the pipe from point 1 to point 2. Or in this equation alone, you can tell delta P equal to shear stress divided by R times L. Okay, this is shear. This is a mathematical model. Okay, this question I'm going to ask Ku, are you there? Ku, are you there?
Yes.
Yeah, looking at this equation at the bottom, I'll just give you a scenario. What happened to the pressure magnitude if you're increasing the radius R? If the R value is increasing, what happened to the pressure? What happened to the change of pressure or pressure difference? Will the delta P increase or decrease? If you increase R, if R increase, what happened to your delta P? Will it increase or will it decrease?
Increase.
You understand the question, right?
Oh, yeah.
We are increasing R, right?
Yeah.
So meaning your R here is increasing. You know how to do mathematics, right? This is the standard 3, not standard 3. This is yeah, your PMR, not PMR, standard 6 equation. Increase R value, what happened to a delta P?
Decrease.
Okay, so be careful. This is
Okay.
one of the fundamental equation that we're going to test you in lots of question. We're going to ask you what happened to when you increase R, what happened to the delta P. It means if you increase, what the question will look like this. What happened if the engineer changed to a bigger pipe? What happened to delta P? If all the parameters remain same, I only change the bigger pipe, what happened to the pressure drop inside the pipe flow? You increase P, this one become bigger, right? This one bigger, meaning the whole magnitude will drop. Pressure difference will drop when your delta P becomes smaller. What happened to your Q? What happened to your Q? You try to logical think. Your delta P is the pressure difference 0.1 and 0.2. And the difference of P1 and P2 drop. What happened to your Q? The flow will become faster or slower? Cool, what do you think? I keep asking you about the pressure, right? In the beginning, you know to have a flow, to flow inside pipe, you need higher pressure at 0.1, right? Is that cool?
Yes.
Yeah.
Yes.
Now, the scenario, I give you a scenario. Let's say the engineer or the technician accidentally change the pipe size, become a bigger pipe, means R increase. So R increase, this whole products will become smaller. Delta P will smaller. So the change of pressure will drop. So what happened to the velocity? What do you think? The Q, what happened to the Q? What happened to the Q? Will the flow faster, or the flow will flow slower?
The velocity will drop.
Velocity drop, huh? So this is all the logic thinking that you should develop when in your third year already. So we are expecting you able to see the effect when you change something. When you go to job later on, go to work later on, when you in your project, when you handle a project, most probably this kind of thing you need to pay a little bit attention. Okay, especially when you change the pipe size and the dimension of your design. It will reduce the pipe flow. It will affect the pipe flow. Okay, so again, using the similar thinking, what happened if the engineer, a junior engineer, accidentally use a smaller pipe? What happened to the flow? So you do the same thinking. I think you're able to answer. Okay, if you're able to answer, means you understand F equal to ma. Second Newton law, what happened if you use this ratio? Okay. Okay, I'm going to move a little bit fast. So we already agree, we have delta P divided by L equal to 2 shear divided by R. So let's say we have a shear stress in a ratio of R. What does it mean? If you rewrite this equation, delta P divided by L, and you pull your R to the left-hand side, you get, and divided by 2. 2 you pull to the left, divided by 2. You get 0, right? So pressure is a constant value. Length is a constant value. And if you want to study the relationship between R versus shear, this whole thing divided by 2, constant, you can write constant R equal to shear. This is how I write the note here. Okay, so the capital C here represent delta P divided by 2L is a constant value. So from here, we're able to develop the relationship. Okay, I'm going to move fast. When you develop equation, one of the strategy is we use boundary condition. Boundary condition means that we look at R equal to 0, what happened to the shear? R equal to the wall, what happened to the shear? So let's look at the first boundary condition. R equal to 0, which is here. R equal to 0 at the center. Shear equals 0. Why shear 0? Because the flow at U max at the center. There is no friction in the center. So 0. What happened if it's near to the wall? At the wall, pipe wall, there's a friction there. So wall R equal to D divided by 2. You take diameter divided by 2. You will get the shear max value, friction maximum at the wall. Okay. Any one of you not clear of the boundary condition that we mentioned on the top of the screen here? Make sure you understand the logic behind the boundary condition. Then we can write in this way. At R at the wall, D divided by 2, your shear equal to your wall stress, wall shear stress. Okay, wall shear stress. So we start with the detonation. W means wall. shear at the wall, or you can treat this one as the friction at the wall. Huh? So what we can do here is that you substitute this R divided by 2 here in this scenario. Constant value times R using this boundary condition, you're going to get wall stress equal to constant value D divided by 2. You rearrange the equation. 2 wall shear stress divided by D. You pull the D to the left, pull the 2 to the left, you get the constant value. So your constant value equal to 2 wall shear stress divided by D. After that, you get your C, substitute back. You will get the equation. We start developing the equation. As you can see, we substitute back here. Your shear stress will equal to 2 wall shear stress R divided by D. Okay. You can come back to this one later. So after that, we combine these two equations. You can find the drop of the pressure when you know your shear stress at the wall. If you're given your shear stress, you can find drop of pressure straight away. Okay. This is another equation. Delta P equal to 4L shear of the wall stress divided by D. All right. Now, a hint to solve the question. Sometimes you need to re-engineer the question. What happens if there is no viscosity? Means no friction. If no friction, or viscosity is like the resistance to flow. If there is no resistance to the flow, means there is no shear reaction. This arrow will become 0. There's no fighting force to the flow. So when there's no viscosity, shear equals 0. So substitute this one 0. What happened to the pressure? The change of pressure? Cool. What happened to delta P if there's no viscosity? What happened to this equation? If no viscosity, what happened to your delta P? Equal what? Cool. Are you there?
Same 0.
0. So what mean by delta P 0? What mean by delta P 0? Again, go back to the pipe question that I asked you since the beginning. P1, P2. If delta P 0, what mean by P1 and P2? Cool?
No change.
No change. So P1 equal to P2, right?
Yes.
Yeah. So in the pipe flow, if having a pressure, same pressure, what mean to your velocity? Think back, how flow pipe works. If you have the same pressure and the delta P is 0, what happened to your velocity inside pipe? Do you think the flow will flow?
No, same
No,
also.
So it's, be careful using the word same. Okay, the velocity will be 0. Means inside pipe, the pipe will not flow. For a horizontal pipe, for a horizontal pipe, if your P1 equal P2, there will no flow. The flow will stagnant. Be careful when it's no viscosity. V0. Or we can say Q, volume flow rate will be 0. Okay. So these are some concept you need to know. Huh? So delta P 0, so constant. Then what happened to the longer part? Use this one. I'll let you to go and look at the equation. What happened? You increase the length. What happened to the drop of the pressure? Delta P is a drop of pressure or the change of pressure from 0.1 to 0.2. All right, with viscosity in place. What happened if you use longer pipe? What happened to the delta P? Delta P is the pressure between 2 points. Okay, another scenario. What happened if you use a smaller diameter with viscosity? What happened? Okay. Think, all these questions will be tested when it comes to your test or exam. Try to think. All right. Just take note that this equation works for both laminar and turbulent. Meaning, when you solve question, first find Reynolds number. It will give you either laminar or turbulent. Then, if you need to find the entrance length, then you choose accordingly to the entrance length equation, either laminar or turbulent. But if the question asks to find pressure drop between 2 points, whether is laminar or turbulent, same. Either of these three works for two scenarios. Laminar or turbulent works also. Just for your info. Okay, I'm going to go a bit fast. A few more slides about shear stress. So shear stress, you can write minus mu du dr. What mean by u here? U means direction of velocity in x direction. Velocity in x direction. R is radius. Right? Shear is the direction. Shear is the direction along the wall area. But now we look at the distance from center. What happened to the shear stress from center times the viscosity? And why negative there? Why negative? Just read this note because if you increase, if you reduce, okay. This is the center of your pipe, X. If you increase the R, the shear stress will increase because it's near to the wall. And if you reduce the R, then the shear stress will drop. So there's a note here. Negative sign is to give so that your value of your shear stress will always positive. Right? So because the differential of your dr will always will be negative. What does it mean? It means what mean by u again? U is velocity. Velocity in what direction? X direction. Okay. Now you look at the velocity here. Okay, I change color to represent velocity. Velocity at the center, we know that is u max. What happened if you increase the radius from center? What happened to the velocity? Velocity will decrease because you are having a parabolic, fully developed scenario. So maximum at center, as you near to the wall because of friction, velocity at here will be 0 at wall. So when you write mathematics, du over dr means the change of velocity. If you increase the r, will be negative. Means it will become less and less. The magnitude of the velocity will become less and less. Okay, so this one explains why the negative in mathematical term. And we know that the value of our shear will always positive. So that's why we need to add a negative sign there. So that when we calculate later on, we'll get a positive sign for shear. There's no negative. Minimum value for shear is 0. There's no negative sign for shear. Okay. So combine the two equations. We will get, you combine this one into this one. Okay, you rearrange the equation. In du dr, you will get negative delta P divided by 2 mu L times R. Okay, because just now your mu equal delta P divided by 2 mu R. Okay, mu R. Okay, LR. So you times the L inside there, then you rearrange, you'll get this equation. Okay, read back these slides if you don't understand the mathematics. Then after that, you continue develop, because you are having differential equation, you want to find the total velocity. You use integration steps. You integrate left side, right side. You pull the constant value out, because all these are constant value. P, mu is constant value, kinematic is constant value, length is constant value, so you can pull the constant value outside the integration, and you integrate towards R. When you integrate towards R, recall back integration skill. When you integrate with something that do not have limit on here and here, there's no limit here, you will come across the constant value C1. If you don't understand the integration step, go and flip back your advanced mathematics on how to do integration with no limit. You will get R squared plus C1, and the left hand side, when you integrate, you get U. You continue. How do you find the C1? You use boundary condition again. At wall, the location of the wall here, at here, R equal diameter divided by 2. However, velocity at wall will be 0. This mean by this boundary condition. Okay, so in test later on, I will ask you to write the boundary condition in your calculation. This is the boundary condition. Meaning you look at one point, what does the value of velocity? That location usually is represent either R equals 0 at the center, R equal to D divided by 2 at the wall, or R equal to capital R at the wall. You substitute inside here, replace all the value, U here, and no, not U, U0, and R is D over 2. Rearrange, you get C1 equal to delta P over this one. Substitute back here. Rearrange the equation. You get this form. What mean by this parameter in front of the bracket here? It means centerline velocity. So if you want to find centerline velocity at the straight pipe. If the question straight away asks you what is the centerline velocity, you use this equation. What is the R value for centerline? 0. Means you substitute R0 here, cancel this whole thing. You straight away, you will get change of pressure. Change of pressure, I did ask you how to find already. There's an equation just now. D given, mu from the table, length given, you're able to find velocity at the center of the pipe. Okay. So this is VC means center velocity. Yeah. So again, use back the pressure gradient at the wall just now. You managed to find, just substitute delta P inside here. Rearrange, cancel what is necessary. You will arrive at this one. Okay. And we replace the D with R. R is D divided by 2. So we replace R divided by R squared. So as you can see, this slide shows you how we change the equation from this form to this form. Then after that, this equation is what you seen in chapter 2, where you're having a parabolic shape, mu D divided by 2 dynamic viscosity, 1 minus R divided by capital R divided by 2, represent by the parabolic profile. Okay, so this slide proves this equation for parabolic flow with a VC at the center. Okay. Okay, I think we stop here. We continue in next lecture.